When a spectrometer acquires continuously with a very short integration time, processing, displaying, or saving every spectrum immediately may become unstable. USB transfer and host processing delays can then cause spectral data loss. The OTO ring buffer first stores continuous spectra in the spectrometer's buffer memory, and the computer retrieves them in batches. This reduces the number of transfer calls and improves the reliability of high-speed continuous acquisition. This video explains the ring buffer concept, key parameters, data fields, and important precautions. It then demonstrates the complete workflow with a Python example. A ring buffer can be viewed as a circular storage area whose end connects back to its beginning. This animation specifically uses 64 storage blocks as an example. Light green represents space that is available for new data. Whenever the spectrometer completes a new spectrum, it writes the spectrum into the next block and changes that block from light green to yellow. Yellow represents continuously stored spectra that have not yet been transferred to the computer. When a group of spectra is prepared for batch transfer, those blocks change from yellow to blue. Blue means that the data is being prepared for transfer to the computer. Only after the blue data has been read and transferred may the corresponding blocks return to light green and become available again. After the 64th block is written, the next spectrum returns to the first block. The host retrieves a group of consecutive spectra according to the configured block length. This design allows an OTO spectrometer to acquire continuously while reducing the number of USB transfer calls. The host must still read fast enough to prevent the available space from running out. Before using ring buffer, understand three important parameters: buffer size, block length, and ring average. Buffer size is the total space available for temporary storage inside the spectrometer. The number of spectra that can be stored depends on the model, frame size, and device memory. Always use the value reported by the SDK. Block length is the number of spectra the computer retrieves from ring buffer in one call. According to the SDK rules, this value must be a multiple of 2. A very small block length increases the number of USB calls. A very large value increases the waiting time and host processing load. Ring average specifies how many raw spectra are averaged into one output spectrum. When average is greater than 1, the number of output spectra decreases. Block length, frame number, and the application array size must therefore be checked together. Larger values are not automatically better. Select a stable combination based on integration time, processing speed, and application requirements. Now focus only on the first two fields in the ring buffer output, pixel 0 and pixel 1. When average equals 1, pixel 0 is the output spectrum index, which identifies each output spectrum. Pixel 1 contains the acquisition timing information for that spectrum. When average is greater than 1, pixel 0 remains the output spectrum index. Pixel 1 becomes the raw spectrum index, which identifies the raw spectrum associated with the averaged output. In this case, compare pixel 1 between consecutive outputs. Under normal conditions, the difference should equal the configured average value. If it does not, check whether raw spectra were lost between the two outputs. Before development, confirm 5 important points. First, ring buffer only provides temporary storage. It does not replace continuous reading by the computer. The application must call the acquisition function reliably so that unread data is not overwritten. Second, block length must follow the SDK rules and match the dimensions of the receiving array. Third, average changes both the output count and the meaning of the leading fields. The receiving array and index checks must be adjusted accordingly. This tutorial focuses only on pixel 0 and pixel 1. Fourth, use UAI spectrometer set frame number to configure the maximum number of spectra stored in the spectrometer, and use UAI spectrometer get frame number to read the value back for verification. Fifth, check the return value or error code after every SDK call. When the program ends or an exception occurs, stop ring buffer first, and then close the spectrometer connection. Before reviewing the Python code, use this flowchart to understand the complete ring buffer sequence. First, connect the OTO spectrometer and obtain the device handle required by subsequent SDK calls. Second, retrieve the raw frame size and prepare the wavelength and intensity arrays. Then retrieve the raw wavelength array within the valid spectral range. Third, use frame number to configure the maximum number of spectra stored in the spectrometer, and then set the integration time. Fourth, configure block length to determine how many spectra the computer retrieves from ring buffer per call. If required, also configure ring average and whether boxcar processing is applied to the output spectra. Fifth, set the block mode start-stop control value to 1 to start ring buffer. After ring buffer starts, the application repeatedly calls block data acquire to retrieve stored spectra in batches. After every acquisition, the program decides whether to continue. If it continues, it returns to the acquisition step. To finish, set the control value to 0, stop ring buffer, and then close the device. The Python example first uses types to load the OTO SDK. Windows loads user application DLL, while Linux loads the corresponding shared object. Next, use the common device connection routine to open the spectrometer with the specified VID and PID, and obtain the device handle. All subsequent ring buffer APIs require a valid handle. If opening the device fails, stop the workflow immediately and report the error. After the connection succeeds, retrieve the raw frame size. Then use that frame size to prepare the wavelength array and the number PY array that will receive spectrum data. After retrieving frame size, read the raw wavelength array so that spectrum data can be mapped to wavelength values. Next, call set frame number to configure the maximum number of spectra stored in the spectrometer. After setting the value, call get frame number to read it back and confirm the setting actually used by the device. Then configure integration time, which is the exposure time for each spectrum. Next, configure block length to determine how many spectra are retrieved from ring buffer per call. This value must be a multiple of 2. If averaging is required, configure ring average. Otherwise, keep average equal to 1. Finally, allocate a receiving array with the correct dimensions based on block length, average, and frame size. After all parameters are ready, set the block mode start-stop control value to 1 to start ring buffer. The SDK requires contiguous float memory. The number PY array must therefore use the correct data type and shape before its pointer is passed to the API. Then enter the continuous acquisition loop. Each call to block data acquire retrieves 1 block of spectra from the device. After every acquisition, first check the API return value, and then read the spectrum index from pixel 0. If average is greater than 1, also compare the raw spectrum index in pixel 1 and verify that the difference matches the average setting. Spectrum data can be passed to display, analysis, or file output. These tasks must not block continuous ring buffer reading. When necessary, send the data to another queue for background processing. During continuous acquisition, check the error code and confirm that the receiving array shape matches the actual block length, average, and frame size. If spectrum index or raw spectrum index contains an unexpected gap, first check the host reading and processing speed. Then adjust block length or other parameters if required. Use try and finally so that the cleanup sequence always runs. When finishing, set the control value to 0 to stop ring buffer, and then close the OTO spectrometer. Finally, review the complete OTO ring buffer workflow. Connect the spectrometer and retrieve frame size and the wavelength array. Configure integration time, frame number, block length, and the required average function. Start ring buffer and use block data acquire to read spectrum batches continuously. After each acquisition, use pixel 0 and pixel 1 to check the output index and raw spectrum index. When the program ends, stop ring buffer before closing the device. Continuous and reliable host reading, correct array allocation, and index validation allow ring buffer to improve the reliability of high-speed continuous spectrum acquisition. This concludes the OTO ring buffer concept and Python development workflow.